Hello everyone, and now we'll start our project proposal. And nowadays, high-stakes settings like loan approval use machine learning tools to help make decisions. But then how can we ensure that ML algorithms to make fair decisions? And how do we guarantee that? Historical discrimination actually affects the ML algorithms to produce biases and disadvantages over protected groups. For instance, Compass is a popular commercial algorithm used by judges and officers for scoring criminals' likelihood of reoffending. And cited from ProPublica, black defendants were actually often predicted to commit recidivism than they actually were. So this is a biased situation. So various fairness metrics were proposed to make fair decisions. For the first one, demographic parity. Example shown below for group A and B, if the school admission rates are same, the demographic parity is satisfied. However, what if group A is on average more qualified than B? Then this must be an unfair situation. So for the second metric, when we know the ground truth, we can see the accuracy of prediction. So if the prediction accuracies are same in both groups, then the accuracy parity is satisfied. And this metric can support the drawback of demographic parity. However, consider a case like for group A, prediction only good at rejecting unqualified students, and for group B, prediction is only good at admitting qualified students. So many qualified students are not properly admitted in group A, and many unqualified students are not properly rejected in group B. So even though the accuracies are same across two groups, this must be unfair situation. So for another one, equalized odd is proposed. It is satisfied when the true positive rates and false positive rates in each group are same. This metric can support the drawback of accuracy parity, but obviously there exists some corner cases in this metric as well. So this is a problem we are tackling in this project. So for a fairer decision, can we satisfy multiple fairness metrics together? So if it's possible, how can we design the ML systems to do so? There are tons of existing works to achieve various fairness metrics. When we only consider the demographic parity, we cannot achieve perfect classifier when the base rates of two groups are different. To solve this problem, some works try to learn accuracy parity, but forcing only accuracy parity also incurs some problems. Thus, Mandras et al. Has tried to use equalized odds as a metric for learning fair representation. However, forcing the single metric always has some limitations. To tackle this issue, Zhao et al. Has proposed to satisfy both accuracy parity and equalized odds. And in another perspective, recently, using adversarial training has emerged as promising strategy to train fair representation. And these are the work using adversary. And among this work, we decided to replicate this work since this work tried to minimize multiple fairness metrics together.
So the main research question of the paper is that, is it possible to simultaneously guarantee equalized odds and accuracy parity? And to answer this question, they use adversary to learn fair representation and use balanced error rate with conditional alignment of representation. As a result, the proposed method achieves both accuracy parity and equalized odds without impacting demographic parity. And meanwhile, it achieves multiple fairness metrics with no harm in utility, or so-called as prediction accuracy. And this is the core of this paper. From the conventional adversary in learning fair representation, here it proposed new objective to mitigate trade-off between utility and fairness. And we will reproduce the experiment done by the authors as follows. With these comparison methods, we will measure gaps in fairness metrics and utility to prove that this work can achieve multiple metrics at the same time without harming utility. And this is the expected results. The green line is the line for a proposed method, and rest of the lines are for competitors. So we will try to reproduce this result. but it has a critical limitation in imbalanced datasets, such as adults dataset as shown in the above figure. Although the proposed method achieved the lowest accuracy parity, it should sacrifice utility to achieve those accuracy parity. So to solve this issue, we will try to exploit another fairness metric, counterfactual fairness, on top of proposed objective function. As a mean of augmenting the individual sample, it may introduce more robustness to utility and thereby lead to less joint error in imbalanced dataset. So basically, our goal is to retain both accuracy parity and equalized odds in imbalanced dataset with only less harm in utility, even in imbalanced dataset. For data, we will use COMPASS and adults dataset, which are popular datasets in ML fairness. In COMPASS dataset, each instance contains 12 attributes, including age, race, gender, and etc. And goal is to predict whether a criminal defendant will recidivate within 2 years or not. Similarly, adult dataset has several instances describing adults, and goal is to predict whether income exceeds $50,000 per year based on census data. For weekly plan, we will use first 2 weeks to set up the environment and find related resources. And from 9th to 13th weeks, we will start producing the paper. We will first reproduce the proposed method and then the competitors for comparisons. Then we will improve our system with counterfactual fairness until 15th week, and finally, a final presentation will be done on our last week. So this is end of our presentation. Thank you.